In this video I want to continue to look at writing Java classes, and in particular now turning our attention to writing methods. And throughout this video I really want us to think about the structure of Java methods, observing the structure of Java methods, what they look like, because they have a very strong structural pattern to them that by observing we can gain confidence in writing the source code associated with our own methods. So let's review what we thought about in the last video. We've said that class bodies contain fields, constructors and methods, and that fields are used to define what are called instance variables, the variables that an instance of the class has, and those instance variables store values that determine an object's state. And then the role of a constructor is to initialize an object when it's first created, so that those instance variables contain their initial values ready for the object to do its job via the method calls that it receives throughout its lifetime. And we met our first Java statement, which was called an assignment statement. I introduced the assignment symbol, and an assignment is used to store a data value into a piece of memory associated with a variable. And we'll meet various kinds of variables throughout this course. Instance variables are one type of variable, parameters are another type of variable. So in an assignment statement we have a variable on the left hand side of the assignment symbol, and then some expression on the right hand side before a semicolon. The expression is evaluated and the resulting value stored in the variable on the left hand side. Now, in our first step of thinking about the structure of methods, I want us to think about the overall structure of a class, and that structure is implicit. In other words, you don't actually have to lay out your Java source code in any particular way, and depending upon how you do lay out the source code, you can either reveal or obscure the structure of a class, or the structure of a method, or the structure of the contents of the method. So, for instance, the source code here of a little bit of the ship class is perfectly valid Java. You could type that into a class definition, ask the compiler to check it, and it will say, yes, everything's fine. The problem is that that sort of layout is very difficult for a human reader to read and understand and comprehend, because it's obscuring the inherent structure of a class definition. So we tend to apply various rules for laying out source code, and although different people have different ways of applying those rules, generally they're applied in order to reveal the implicit structure of a class, or to recognize the structure of a class. And one way of thinking about it is to think of a class definition as actually being two-dimensional, rectangular in other words, and that outer wrapper of a class, the class header, that pair of curly brackets, is like a box that's going to contain various other definitions inside it. So inside the definition of a class. So think of a class as being a 2D structure, a container, if you like, for fields, constructors and methods. So another way of visualizing that is to say that inside that outer box of the class wrapper we're going to have some fields, which again we can think of as a little bit like a box. We'll have one or more constructors, and each constructor itself will be a box that can contain other things. And then we have some methods, which again are boxes. So making that a bit more concrete, here's our ship class. There's one of its fields, speed field. There's its constructor. And inside the body of the constructor, in between its own pair of curly brackets, we've got an assignment statement. Now, BlueJ actually tries to help you in recognizing this class structure by using background coloring underneath the text of your source code. So in looking at Java classes, you might not have appreciated what that coloring is trying to do, but it's doing just that. It's trying to show you which parts of the class really belong at which levels of the two-dimensional structure. So something for you to observe as you look at more Java source code is look at how the BlueJ editor is showing you the structure using that kind of highlighting. So on to methods. What are methods? It's really the final member of a class that we need to think about in detail at this stage to add to fields and constructors. So once we've got those three members, then we can start to really get on and write significant amounts of Java source code that are highly functional. So methods are a way of providing other objects within a program of ways to interact with our objects. So up to this point, we've not really thought very much about the context in which an object operates inside a program. We've been a human user interacting directly with an object on the object bench within BlueJ. That's an artificial kind of setup. And what we really need to do is move our thinking on and say that when I'm running a program, I might have tens, hundreds, maybe even thousands of objects running, and those objects wish to communicate with one another. Those objects wish to pass information to each other. Those objects wish to ask questions of other objects and receive answers, where the answers are really data values returned from other objects. And the way that objects communicate with each other is they call each other's methods. So methods provide ways for other objects to do things like ask an object about its state. And when an object replies to a question about its state, it's typically able to return information about just one of its instance variables, one of the values of one of its fields. Another way in which objects interact is that one object might ask another to change its state. And in contrast to when an object returns information about its internal state and returns only one value, a call to a method that changes an object state may end up changing multiple aspects of that object state. So in other words, change multiple instance variables value. And a third way in which objects interact is that one object might call a method simply in order to ask another object to do something. For instance, to print a ticket from a ticket machine. So one of the things we'll see is that when we define methods, some of the methods we define will take parameters, in other words, receive information as part of the method call, and methods might or might not return results. So they might give an answer to a calling object, or they might simply perform some action and not return any data value to the calling object. Now, one of the things that's a little bit tricky in the early stages of learning how to program and writing methods is the appreciation that there's a difference between what we see when we read the code of a method, and we say that's really a static textual description of an object's runtime behavior, and what actually happens when that method is called. In other words, what happens at runtime, which we say is the dynamic behavior of a method. So it can be difficult in reading the static text to appreciate just what's going to happen when that method is executed. But that's something you'll gradually get to understand and learn about as you understand the different kinds of method bodies that we'll be dealing with, the kind of statements, the kind of actions that methods have within them. But a really important point to take on board is that methods are not mathematical functions. So if we think about a mathematical function like square root, for instance, we want to find the square root of a number. The square root of the number 16 is 4. Well, if we were to pass 16 to a square root function, every time we did so, it would always return the same answer. Methods are not like that. We can write methods that implement mathematical functions and that will have that kind of behavior, but it's much more common that when we call a method, the result of calling that method will depend not solely on any parameters that we pass to it, but upon the state of the object on which we call the method. So it's important to break any connection you might have in your mind between the idea that a method is somehow like a mathematical function. That's not the way that methods work. Now, one of the things that we'll see as we look at the structure of the source code for methods is they look quite like constructors, and we've already seen the source code patterns for constructors. So we know that a constructor has a header and a body. The header may include parameters, and the body of the constructor contains statements or actions. And similarly, what we'll see is that a method also has a header and a body, and a method's header may include parameters, and a method's body will contain statements to carry out the actions of the methods. So although superficially constructors and methods will look quite similar at a source code level, they're actually very different, and there are some differences at the source code level that we need to pay attention to. So again, it's this idea of observing very carefully what we see and then imitating what we see, and being careful to distinguish between how constructors look and how methods look. So what are some of the similarities and differences? So a constructor always has the same name as its containing class. But a constructor can only be executed while an object is being created. And the clue's in the name. It's called a constructor. So the idea is that when we create or construct an object, that's the point at which the constructor kicks in, performs its action, and then for the rest of the object's life, the constructor really plays no part in that at all. So a constructor's role is purely to initialize an object's starting state, and thereafter its job is done. Another important point, whose meaning will become clear when we've really looked at methods in more detail, is that a constructor cannot return anything. So we can't ask a constructor for any information. We simply say to the constructor, initialize this object, and then that's it. And if we want to find out any information about, for instance, the initial state of the object, then we'd have to use methods to do that. So what about methods? Well, a method has a name that's related to its specific purpose within the context of the class. So triangle we saw has methods like move left, move down, change color, and so on. Ship has methods like set course, set speed, get position, and so on. So those names are chosen because they reflect the purpose that those methods are fulfilling within the context of the class. Unlike constructors, which are only called when an object is being created, a method can be called at any time. Once an object's been created, then call the method whenever you like. All methods are available all of the time. And if defined appropriately, and we'll look at what that means in a moment, a method can return a result. So another object can ask an object, please give me some information, maybe calculate something for me and return the answer, or tell me what the value is of this particular instance variable that you're storing. So a method can return a value if defined appropriately. So let's now begin to look at the source code structure for methods in Java. Firstly, we'll start with the header of a method. So here we've got the header of the method moveLeft taken from a triangle class, and the header tells us four things. Firstly, the word public tells us what the visibility of this method is to objects of other classes. So a method that's defined as public may be called by objects of any class that we choose to define. It's a public method. We could have defined the method as private. We're not going to see any examples of private methods within this session, but had we used the word private instead of public, then that would have limited the visibility of this method, and objects of other classes would not have been allowed to call it. Calling that method would have been limited to objects of its own class. For the most part, we'll see public methods in this initial discussion. The second element of the header tells us whether this method is going to return a result or not, whether it's going to return a data value. And in this case, the moveLeft method simply does something to the triangle state, and it doesn't return any kind of result or answer to the caller. So in that case, we use the word void to mean that no data value will be returned by this method. The third element of the header is the name of the method, and we've chosen a name that clearly relates to its purpose. You might notice that we've started the name of the method with an initial lowercase letter, and that's a convention that will follow throughout this course. We'll always start method names with an initial lowercase letter, and that's a convention you should aim to follow because that's what Java programmers do. But where the name of a method appears to be composed of multiple words, like move left, go up, set course, and so on, it's a common convention to use an uppercase letter for the first letter of the second, the third, the fourth word in the name of the method. So there's no space between the word move and left. It's all one word, move left, but in order to make the name of the method slightly easier to read, we use this form of capitalization, which is sometimes known as camel case. The idea is that camels have humps in the middle, and the effect of having uppercase letters embedded in the middle of a method name gives a slightly camel-like look. So we call this camel case. Very common convention used by Java programmers, and I'd encourage you to follow that kind of convention. And then immediately after the name of the method, we have a pair of parentheses. We always have to have a pair of parentheses, whether the method takes parameters or not. And in this case, because those parentheses are empty, we know that when the method is called, we don't have to pass any extra information in. So we saw when looking at constructors that if we wanted to create a ticket machine for a particular price, we had to pass that information in, and in the header of the ticket machine's constructor, we had to define a parameter in between those parentheses. So we could put parameters in methods if we wish to do so. In this case, the move left method doesn't need a parameter, so there isn't one in there. Let's look at another example of a different method with some different characteristics. So this method does have a parameter. Hopefully from your observations of the move left method, you understand the first three elements. Public, so the method's accessible by objects of other classes. Void, it doesn't return a data value. Insert money, again following the camel case idea, initial lowercase letter. The second word, money, has an uppercase M, and then we've got a pair of parentheses, and this time between those parentheses we're saying that when this method is called, a value must be passed in. So some money is being inserted into the machine. How much money is being inserted? Well, the exact amount of money on any particular call could be anything. And what that variable called amount does is it contains the particular amount of money that is being inserted on this particular call. So it receives a parameter value, a numerical parameter value, and that numerical value is then going to be used inside the body of the method. So between the curly brackets we have an assignment statement. We can see that clearly there's the assignment symbol immediately after the word balance. So the assignment says on the right hand side, go and find out what the current amount of money is in the balance, perform a calculation that then involves adding the new amount of money being inserted to form a new value, and then that resulting value must now be stored or assigned to the memory location named balance. So this is where appreciating that that assignment symbol is not the equal symbol is really important, because in mathematics we wouldn't normally see the same variable on both the left and right hand side of an equal symbol. So it's important to appreciate that that right hand side there is performing an arithmetic expression. It's taking two values, the one in balance, the one in amount, it's adding them together, and the resulting sum is then being stored into the memory location known as balance. So what we have is an example of a method that's changing the state of the ticket machine object that the method is being called on. And we say that this method is mutating the state of a ticket machine object. So this is an example of a method that changes or mutates the state of an object by receiving a parameter value and changing the value of the instance variable balance. It's really important that you understand what you're seeing here. So all the elements of the header, what's going on inside the body, and the resulting effect that will happen on a ticket machine object. So far we've seen two methods, both with a void return type, so in other words not returning any data to the calling object. Let's now look at one which does in fact recall some information to the calling object. So imagine that sometimes an object might want to ask a ticket machine, well, what's the price of tickets? So in order to do that, we need to write a method inside the ticket machine class that can return the current value of tickets. In other words, what value is stored inside the price field. So reading the header again, we see the word public. So this method is callable by objects of other classes. But then instead of seeing the word void, we see the word int. So this method has an int return type. In other words, when this method is called, it will return an integer value to whoever called it. Then we've got the method name getPrice, then a pair of empty parentheses, so when getPrice is called, it doesn't receive any information coming in. It's purely asking for information from the ticket machine. And then inside the body of the method, in order to fulfill the requirement that the method returns some information, we've got what's called a return statement. We write the word return, followed by any expression whose type matches the return type of the method, and then a semicolon. And in this case, we don't need to perform any calculations. We're simply interested in knowing what value is stored in the price field, how much the tickets cost. And so the value from the price field is returned from the method. And any other object wanting to know how much the tickets are from this ticket machine will receive that information. Now, it's important to appreciate that returning is not the same as printing. So remember, what we're doing here is we're writing methods that allow objects to communicate. And typically an object is not interested in another object printing something, because printing is for humans. Printing appears on the screen or appears on a printer. Returning a value from a method means that some data value is passed to another object so that that other object can do something with the data value. Now this type of method is very common. It's what we call a getter or an accessor method. So an accessor method, a getter method, always has a return type that is not void, because by its very nature it's going to return a data value, and void means it doesn't return a data value. So accessors always have a non-void return type. So the method will always contain a return statement that fulfills that requirement, and that return statement will return a value of the type whose name is given in the header of the method. And just to restate, that returning is not printing, it's passing a value back to the caller of the method. So it's very common for fields to have an associated getter method. And once we have a definition of a field, it becomes very easy to write a getter for it. So they have a very simple distinctive form that arises directly from the definition of the associated field. So the return type of the getter is going to be the same as the type of the field whose value we're returning. The method name is related to the field name. It will typically be get and then the name of the field, but again observing the camel case convention that that second word will have a capitalized initial letter. Getters typically take no parameters because they're purely used to return information, not to receive information. And the body of getter methods typically consist of a single return statement and nothing else. So here's an example. Here's a getter for a speed field. So if we have private int speed, the getter is very easy to write. We know that the return type is going to have to be int because that's the type of the field. We know that the method's name is going to be getSpeed because the name of the field is speed. And we use the camel case capitalization of S in getSpeed. It takes no parameters, so those parentheses are empty. And then the body of the method simply contains a single return statement, return, and then the field whose value we want to return, and then a semicolon. So it's good to observe that pattern, and then I want you to imitate that pattern for the fields that you write that require getters. Not all fields require getters, but many do, and this is the standard form to use. Let's say a little bit more about mutator or state changing methods. So, as the name suggests, these are used to change the state of an object, and they do that by changing the value or values of one or more instance variables. So therefore they typically contain one or more assignment statements, because assignment statements are the way that we change the value of a variable. And they often, but not always, but they often receive parameters whose values are then used to make adjustments to the current values of the instance variables whose values we're going to be changing. And just as we saw with getters, it's quite common for fields to have a dedicated set mutator method. And once again, they have a very simple distinctive form. The return type will be void because this time the idea is the object is carrying out an action on its state. So it's not returning some information, it's being asked to change something. Again, the method name will relate to the field name. It will be set something, whether something is the name of the field, with appropriate camel case changes. And then these methods will typically take a parameter whose type is the same as the type of the field being changed. In other words, these methods are being used to overwrite the current value of an instance variable with the value of the parameter being passed in. And then the body of the method contains a single assignment statement to the associated field. So for instance, here's an example setter method. It's got a void return type. It's called setDiscount, so we can infer that it's being used to set the value of a field called discount. It's taking an integer parameter, so we can infer that the type of the field is int. And then a single assignment statement taking the parameter value on the right-hand side of the assignment, assigning to the variable on the left-hand side, which is the name of the field. So we can easily infer that the field must be private int discount. All of the clues are there in the definition of the setter method. Now there's an important principle about setter methods, and that is that a setter method doesn't have to unconditionally make an assignment to its field. In many cases, what we want is for the body of the method not simply to contain an assignment, but to check the value of the parameter coming in to see whether it is actually reasonable to make the assignment. So we often say that these setter and mutator methods protect the values of the fields that they're designed to change. And in this way, they support something called encapsulation, which we'll have more to say about within due course, and the way in which mutators can do that protection we'll say more about as well. So let me give you an example. For instance, suppose we wanted to insert some money into the machine, so that's a mutator method. It's not a setter method, but it's a mutator method, and the parameter value coming in contains a negative numerical value. It wouldn't be appropriate to add a negative value to a balance field, because that would reduce, supposedly, the amount of money inside the machine that the customers put in, and that would clearly be an error. It only makes sense to add a positive value to an existing balance so that the customer has put some more money in. And so the body of the insert money method might actually check to see whether amount is a positive value before making the assignment. And there'll be other situations where even setter methods would check the values of parameters coming in and saying, is the value that I've received reasonable for the purpose of this instance variable? And if it is, it goes ahead and makes the assignment. If it isn't, then it will not make the assignment, won't change the state at that point. So let's review what we've talked about. Methods are used to define the behavior of objects. They have a regular structure consisting of a header and a body. Methods may return a result to their callers, a data value. Methods may take parameters. Not all methods do, but some methods do. And Fields will often have an associated getter or setter method, and we've seen some very simple rules for how to define those getters and setters that fall quite naturally from the definition of the fields that they're supporting. All methods have a return type in their header, and that's either a data type like int or string, or it could be void. If it's void, then that tells us that this method does not return anything. It doesn't return any data value. But if it's something other than void, then that tells us this method will return a value to its caller. And all non-void methods must have a return statement that says what particular value is being returned from this method to the caller.